All right, there we go. So today we're going to continue from what we talked about last time. And last time we were discussing this idea of ill-conditioned and well-conditioned problems. And so there was this idea of thinking about formulating a problem in such a way that, when you start to look at some mapping F of, one way to think about it is from some input to output. We normally think of this as just simply being, y is equal to f of x. So we have some model f that takes me from x, takes me to y. So the idea behind this is that, normally we think of this as just a function call of moving x to y. And then what we talked about in the conditioning last time was to make sure that if we have small perturbations in x, we don't want our answer y to change very much. So if I take this, a well-conditioned problem is such that small perturbations in x lead to small changes in y. An ill-conditioned problem is one which small changes in x lead to large changes in y. And what we talked about is the condition number, and the condition number was related directly for instance, if you make this a matrix operation, which was mostly what we were interested in this class of linear algebra. If this is a matrix operation, then what we're interested in is what is the condition, how do we think about the condition of that matrix A? And I gave the condition number of that matrix A as a ratio of, actually, I think this was just n. If this is a m by n matrix, it was the ratio of the largest singular value to the smallest singular value. So if the smallest singular value is 0, this condition number is going to blow up, and this problem will be ill-posed. And what it's really telling you is that this matrix A then is rank deficient, or another way to say it is the rows of this matrix are basically linearly dependent, or the determinant is 0 of that matrix A. So those are all kind of saying the same statement about conditioning. All right, so that was the idea of what we talked about last time. And now what we want to do is turn our focus to the idea of stability. And this is just as important, which is it is one thing to conceptually talk about a mapping F. And normally we think of this as sort of a continuous variable, all values of x, map through some f to some y. But really, at the end of the day, when we're starting to look at the computer itself is a finite representation of the number line, of continuous numbers. Okay? In particular, any number x, really, when you represent some continuous variable x, it's going to be represented by, going to take on some actual numerical value. And basically, any number representation is going to be accurate to about 16 decimal places. And this is double precision mathematics, or floating point operations, that we've set up in all of our computational architectures. It is a way to represent the real numbers in a computer way. And we basically can represent them down to about 16 decimal places. That's sort of your rule of thumb. Okay, so this here is your approximation to the number you want, right? So you may have a concept of some continuous value of x, but once you compute it, it's actually taking on some numerical approximation to the value you want. And here, this here is the numerical round off in representing that number. Okay? And so really, at the end of the day, when we start formulating this problem, we actually have to start thinking about formulating not as f, which is some continuous variable mapping everything, but let's call this f tilde, which is going to map our x to y's, where this is my numerical approximation to f itself. Okay, so in other words, f is a concept, a continuous variable that I want to represent. F tilde is actually going to be its direct representation of that. And so this gets us into starting to think a little bit about when you have a problem and you want to think about conditioning, you also want to think about, I'm going to actually compute this through some algorithm. And the important thing about that algorithm is the algorithm itself, the idea of the algorithm being stable or unstable. And we're going to give an example of that as we go forward here. Okay? So this gets right at the heart of computing, which is computing is all about approximation. And the approximations are pretty good. It's down to 16 decimal places, but it still has big consequences when you write algorithms, and in particular around your accuracy and around the stability of a given scheme. Okay, so let's go ahead and start talking about things like errors in the context of these concepts here. All right. So first of all, I want to think about two concepts, absolute error and relative error. The absolute error is this. So what it is what the mapping is supposed to be. And this is my algorithm. F tilde represents the algorithm I used to actually approximate what it's supposed to be. Okay? So this would be, in some sense, the difference between what my algorithm produces and what it's supposed to produce. And this here, you want it, of course, to be as small as possible. Okay? And in fact, a good algorithm will take an error like this, and, you know, the hope is that that kind of error is down at 10 to the minus 16. In other words, is that numerical round off, or the numerical precision of your floating point operations on your computer. Okay? There's also a second metric for error, which is the relative error. And the relative error looks more something like this. It is now, again, this difference, but now it's normalized by the actual value of f of x. And again, a good algorithm is one where this thing here, another way to represent that is epsilon machine. So machine epsilon just means, you know, you're down at 10 to the minus 16s. Okay? Now, the idea behind conditioning was that if I have a well-conditioned problem, this should happen. In other words, notice small changes in the problem lead to small changes in this error. Whereas an ill-conditioned problem, small changes here, this would not happen. You wouldn't get, small changes here would mean big changes, and in fact, then this would not be small. Okay? So that's the idea of conditioning. So what we really kind of start wanting to think about is this idea of accuracy and stability, because in the end of the day, we're going to have to start thinking about what kind of algorithms do I use here. I want to, of course, have an algorithm that's accurate, but I also want to make sure when I do a computation of this through an algorithmic way, that the algorithm itself is in some sense well-conditioned. In other words, small changes here lead to, with the algorithm I use, keep this thing small over there. Okay. So these are conceptual pieces, and you can find some of this in Trefethen's book, where he talks about conditioning and stability. And I want to give a concrete example of what I mean by both error and stability. So what I thought I would do is give you an example when we start thinking about solving simple differential equations, which turns out it's going to be very much a linear algebra type problem. Okay, in fact, let's consider computing derivatives of some kind of function. So first of all, I want to start thinking about something like this. I have a function, y of t, plus delta t. And what we know is from a Taylor series expansion is I could look at this function at t by just doing a Taylor series expansion, and I would get something like this. Delta t dy dt plus delta t squared over 2, and then this is second derivative of y at some c dt squared, where c is somewhere between t and t plus delta t. This is an exact formula coming right out of Taylor series expansions. Okay? So oftentimes what this does is gives you a way to think about approximating derivatives, or in particular, what we might want to do is think about what if I want to solve something like this. A differential equation. Okay? Now, if I want to solve a differential equation such as this, then what you can see here is if I start to use dy dt, notice I can pull it out from right here. Dy dt, if I take that y of t over and divide by delta t, then this thing here is going to give me a nice representation of the dynamics. In fact, what you find is what's called the Euler scheme, which is y of n plus 1. And so y at time t of n, let's call that y of n, and y at t of n plus delta t is y of n plus 1. So this formulation is going to give you y n plus 1 is equal to y of n plus delta t times dy dt, which is this f. So you have f at t of n, y of n, plus, here's my, I'm going to drop that term. I'm going to say this is a term that's ordered delta t squared. If delta t is small, the hope is, since that's something small squared, it's smaller than the rest of everything else going on here. So this is one way to what we call do an Euler discretization for solving a differential equation such as this. Okay? So a couple things to notice. So first of all, let's talk about accuracy of this scheme, and then we will talk about the schemes that we might want to use for stability. All right, so what we're going to do then is start looking at this and say, okay, well, when you start to look at this thing here, this here is what I'm going to throw away. That's my error, right? I'm going to drop this term. This is what happens when you do what's called Euler to stepping. And the term that I'm dropping is going to be a local error. And the local error, let's call it epsilon k, is just the term that I dropped here, which is delta t squared over 2, and the second derivative. So let's call it y double prime at c. Okay? So there's this concept of a local error. So in some sense, this is what we're going to be doing all the time in computing, is we're going to basically make approximations and start dropping terms. And in this case here, this isn't even come from round off. This is just simply me trying to approximate what a differential equation stepping scheme would be, which is here. And I decided to drop this. And in dropping that, I have an approximation for how to go to n plus 1 from y of n through this approximation. But this is the mistake or the error I make at each single step. Okay? But there's also a global error. This is the mistake I make every step. And if I take many steps into the future, then what I would have to do is compute a global error, which would look something like this. It is the sum of all these local errors added together. Okay. Or one way to think about it is you could take this as sort of the average of all the errors. And so if you do this, this becomes approximately delta t squared over 2, some average derivative value, called c, times k steps. That's how many steps I took. Okay. Now, k itself is the total number of steps. And so one of the things you want to talk about is if I took step sizes of delta t times k over some interval, let's say I'm solving this thing on an interval a to b, then I have that k itself is b minus a over delta t. I could put that into there. And then this thing becomes, notice there's a delta t here in that k that cancels out one of the delta t's. So you get delta t over 2 b minus a second derivative c. Okay? So you can start to see that whenever we start to actually compute quantities, often we're making numerical approximations to things of interest, and then we pick up an error accordingly. Okay. Now the question wants to, somewhat what you might want to ask then is, not only do I worry about errors that I make here, there is this question about round off, numerical round off, and how important it is. Like, does numerical round off really matter? I mean, it's 16 decimal places. Who cares, right? It's so small. But in fact, it really does matter. And I'm going to show you exactly how. All right. So this is the concept between local and global error. And the important thing I want to point out here is, what does this tell you about the error as a function of delta t? Notice that the local error, it scales like delta t squared, right? So this is like order delta t squared. So it goes to 0 as delta goes to 0. And this here goes like delta t. So what I would suggest is, if you just want to drop your error down, all you're going to do is take smaller steps, delta t. And I'm going to show you that in computing, because of numerical round off, it's not that simple, actually. And in fact, numerical round off doesn't just let you decrease the error as you drop delta t. So let me show you how that works.
Question.
Yes, a question? Yes?
Yeah, so how did you get k equals to b minus a or delta t?
I follow that interval a to b, and I divide this interval up into delta t is my steps that I break this up into, and I say there's k steps.
Okay.
So k times delta t is the span of the interval.
I see.
So
Another.
That was that formula. So this is the full length of the interval. I chopped it up into k pieces of size delta t.
Okay, that makes sense. Another question, for the Euler's discretization, was that the entire function yn plus 1, or was it just the error term?
Oh, the one that did on the bottom here?
Yeah.
That was the total error for all the pieces that I had.
Also, like the part where you mentioned Euler's discretization, what was that the entire yn plus 1 function, or was it just the
Just
O?
one step from
Okay.
yn plus 1, from y of n to y of n plus 1. I take one step in delta t.
Okay.
Yeah.
Thanks.
All right, so let me tell you what happens when you start to think about round off and the role it's going to play, because it's going to start to tell us a little bit about the fact that we have numerical round off and we're working with double precision numbers matters, and that numerical round off can play a role, and then we'll talk about stability. All right, so we were talking about computing derivatives here. So again, one way to think about it is dy dt was something like this. And what we did is we showed that, oh, but wait a minute, there was this round off, which is from the term I dropped. This was the, remember, that was the term that we dropped out of here, which involved the second derivative plus a delta t squared over 2. Okay? And this is what we're going to do. We're going to say, yeah, but I'm going to approximate my derivative by this slope formula, and I'm ignoring all the higher order terms. Now, what we just said is also that this error goes to 0 as delta t goes to 0. But what does numerical round off do? Well, numerical round off tells us that, in fact, I can never actually give you the exact value of this. I can only give you the value of this to 16 decimal place precision. So in other words, y of n plus 1 is equal to, let's call it capital Y of n plus e of n plus 1. And by the way, this little e here, different than that epsilon, this is my numerical round off error. So this is like 10 to the minus 16. So anytime I approximate a number in the computer, it's only going to be accurate to 16 decimal places. Okay, this is again floating point operations in your computational machinery. This is an IEEE, very quickly the community converged in computing down to sort of a standard for how to do computations. And you have this double precision format in which whenever you approximate a number, you approximate down to 16 decimal places. So another way to think about it is, well, okay, so if I go to actually compute this, not only do I have round off error, like from throwing away this term, right? From dropping that derivative term, I now have a numerical approximation error from trying to compute that quantity. So in other words, when I actually try to compute this, I'm going to put this in here, and then what I actually get then is my computation tells me this. When I go to compute this, I get something like this, plus an error term. So now this is my approximation to the derivative. It's these numbers I get from here, plus some error term. And let me tell you what the error is. The error term now is the numerical round off plus this here, which is the truncation. So in other words, my numerical error is going to be e of n plus 1, e of n over delta t minus delta t over 2, second derivative c. And by the way, so that's coming from here, okay? And this here is coming from the numerical round off. So there's two terms involved in producing my overall error. There is a truncation error, and then there is numerical round off. Okay? So in computing, you're always going to have to deal with this fact. Okay, so here's the thing that's kind of interesting, and something that I wanted to point out to you immediately that starts to raise a problem with computing. I want to draw a plot here. Error versus dt. So let's talk about this error, E of n. So here's the formula. And notice the trends as a function of delta t. If we didn't consider round off, what did the global error go like? Well, it went like delta t. In other words, my error, remember before, just the truncation error drops to 0 as delta t goes to 0. So in other words, I can, if I make my delta t smaller and smaller and smaller, this error goes to 0. However, what about my numerical round off? How does it scale with delta t? As delta t goes to 0, what happens to this? Delta t goes to 0, I'm dividing by delta t. The error at some point starts to get very big. In fact, will go to infinity if delta t goes to 0. So my overall error actually looks something like this. What dominates this over here is numerical round off. What dominates this over here is the truncation. So this already starts to tell you something important about computing. Numerical round off shows up, and it shows up here in terms of thinking that you're going to get more and more accurate. But in fact, numerical round off tells you that you better not drop below here, or else, in fact, you're starting to make an error in your approximation simply due to the fact that you have numerical round off at 16 decimal places. Okay, so the story around computing actual quantities in practice is more complicated than just simply saying, oh, just make delta t smaller and everything works out. Actually, that's not true at all. You make delta t smaller, and actually you can get yourself in trouble with numerical round off playing a big role. Okay, so that's this idea of thinking about a problem and it's, in some sense, conditioning. Another ways to say this is if you take your delta t to be too small and way down here, it's ill-conditioned, okay? Even though the theory would say, oh, there's no problem. Well, if I just take delta t small, I can ignore that. But you take delta t small enough, numerical round off plays a big role. The fact that you have floating point operations has a big role to play in terms of determining your error. Okay. So this has a lot to do with conditioning, accuracy. And now I want to turn our attention to the concept of stability, because in the end of the day, what we are really constructing here is an approximation to something. In other words, we're going to generate a numerical scheme to approximate some values. And we're going to do this now, continue on with thinking about differential equations and start thinking about what does it mean to construct a stable scheme. I've already mentioned before when we were talking about QR and when we did Gram-Schmidt, modified Gram-Schmidt, householder triangularization. Why do we have these three different versions? Because we're really interested in the scheme that produces accurate results, but produces a very robust and stable algorithm for producing the some of the results we want. And so let me just show you an example of constructing numerical algorithms to approximate something we want and show you how some algorithms produce for you unstable schemes while others produce stable schemes. And what you always want to work with as much as possible is a stable numerical scheme. So consider the following. Here is like the simplest case to consider. There is a first order differential equation, let's say with some initial conditions, y0. And by the way, if this is the differential equation, there's the initial conditions, you know, the solution is trivial to get, which is y is equal to y0 e to the lambda t. Okay, so I can solve it explicitly. But now let's come to this and approach it from a numerical point of view and start saying, if I have a harder problem and I can't write down the solution, but I still wanted to approximate this on the computer, how would I come up with a scheme to produce for me some approximation to this differential equation? So we've already been talking about this Euler stepping scheme. In other words, you do your Taylor series expansion. And so one way to get this is you would actually find that here's my Euler approximation to this problem. It would tell you this. So here's the F. And from what we had before, all we did is took this delta t over, this here over. So it's y of n plus 1 is y of n plus 1 is equal to y of n plus delta t dy dt, which is lambda y of n. This is it, and I drop that term. So this is my Euler approximation to solving this differential equation. So what does it tell you? My solution, one step into the future, is what it is now, plus a little bit of a correction, delta t lambda yn. Now, what's interesting about this, you have a yn and yn, and this is linear. What's nice about this is I can just basically write this as 1 plus delta t lambda yn. Okay? So now here's the question. I want to go compute this. And in fact, if I start off with some initial condition, y0, which is here, I can get to y of 1. With y of 1, put it here to get to y of 2. So what I've set up to solve this is an iteration scheme, right? I start off with y0 to get to y1, y1 to y2, y2 to y3, and I just can do this and make n steps into the future, okay? And in fact, if I take n steps into the future, what you end up getting is y of n is equal to 1 plus lambda delta t nth power y0. And I'm just applying this formula n times starting from y0. So here's the question. Is this a stable scheme? And how do I think about stability? And so what I want to do is, in a stable scheme, if this is my iteration scheme for computing the solution, the future state of the system, n steps into the future, what I want to know then is, all right, fine, if you want to do that. So how would this happen? Well, what you would do is say, well, y0. What I would do is actually, when I do the actual computation, I don't really have y0 here. I have some approximation to y0. So I'd actually have some numerical round off here, epsilon. So the y0 is what I start with. So now I perturb this, right? This is some number like that's very small, right? It's numerical round off. So I don't start with my initial condition. I want an initial condition, but I have an approximation to it, which is accurate to numerical round off. And then I ask the question, all right, if I start putting them in here n times, I can ask the following question: what happens then to the error just from a numerical round off on the initial data? The error for that, this is linear, so I can just say, well, the error for this is just going to be 1 plus lambda delta t to the nth power times e. Okay. Presumably delta t here is a positive quantity. So then you're just going to ask the following question: what happens to this error as I take many steps into the future? Well, it's pretty easy to see. There's two options for you here. Option 1, 1 plus lambda delta t. So the absolute value of this is less than 1. So if the absolute value of this is less than 1, and I'm going to take it to the nth power, then I'm multiplying a number that's less than 1 by itself over and over and over again. And then this thing here, then, the error will go to 0. Okay? E goes to 0. However, What happens if the absolute value of 1 plus lambda delta t is bigger than 1? If this is bigger than 1, I'm going to take a number bigger than 1 and multiply it by itself over and over and over again. And this will go to infinity as n goes to infinity. So in other words, in this situation, this fundamental time-stepping scheme that I used here, which was Euler, is actually a numerically unstable scheme. Why? Because any small perturbation leads to the error growing to infinity. So this is sort of like a canonical example of what it means to have an unstable scheme. A small perturbation leads to huge errors, okay? All coming from, essentially, I picked a bad scheme. That's one way to think about it. So this is problematic. It's exactly what you don't want when you're looking at a numerical scheme. You do not want this to happen. Something like this will simply take your scheme, will start to make errors grow, simply because, in some sense, what this is my model F tilde that we've been talking about. Remember, F tilde is an approximation to F, which F is supposed to be the actual solution to this. And when you apply this algorithm, which is an approximation to it, notice what happens in this case here. You go to infinity. Okay? So that is an unstable scheme or an unstable algorithm. Okay? So I want to contrast this with a second method. I'm going to change this around slightly. Okay? So check this out. How would you stabilize such a scheme? In other words, I'd love to do this problem, but then I don't want it to be unstable like it is currently, like the algorithm suggests it is. So here's what we're going to do. We're going to come back a step, erase all this, and in some sense, it is well known, by the way, if you've had any differential equations, numerical differential equations, you'll know that the Euler scheme is generically an unstable scheme. Nobody uses forward Euler because essentially if you put your numerics in it, it eventually blows up, right? And in general, if your scheme is such that generically things are going to blow up, you don't use it. It's a bad model. It's a bad algorithm approximating something that shouldn't be doing that, okay? So we're going to come back to here and start talking about our Euler discretization. Notice what we did. We said, okay, I'm going to approximate the derivative dy dt, right? I mean, this was just the way we did this, right? Another way to write that was we just used our slope formula. There it is. And then I just multiplied dt over here and took the y of n over, and that's what I got here with. What if instead I made a small correction to the algorithm? And here's the small correction. I'm going to evaluate the right-hand side. Remember, this is my f of y. Notice what I did. I implicitly assumed when I took this at a certain time step, I said that this y was evaluated at time n. What if instead, since I'm working on the interval n to n plus 1, what if instead I said, what if I evaluated this at time n plus 1? I can do that, right? This is a different scheme, but now I'm going to say, I'm going to take the same scheme. Here's my derivative calculation. That still holds. But instead of on the right-hand side evaluating at y of n, I just evaluate it at the end of the interval y of n plus 1. Now, the reason we do this now is now I have this scheme, and this was called backward Euler. Because I'm using the forward time here. But notice the tremendous difference of what happens. Before, this was y of n and y of n. I could take it out and combine them. But now I have y of n plus 1. My other y of n plus 1 is here. And so what it sets up for us, if I just do the algebra, it sets up a scheme which is y of n plus 1. Sorry. So if I do my iteration scheme from like we did before, you get 1 over 1 minus lambda delta t to the nth power y0. And all I did was took this, combined it with this, and then use my initial condition to get my basic iteration scheme. So notice, these are just two approximations to the same problem. Algorithm 1, Euler. Algorithm 2, backward Euler. They're both two algorithms trying to approximate the same thing. But there's a tremendous difference in what happens in the approximation in these algorithms. When I write down this backward Euler, notice that my error now, if this thing is not y0, but it's a numerical approximation to some y0, my error term now is going to look like this. 1 over 1 minus lambda delta t to the n epsilon. And so all I care about is, well, 1 is this quantity bigger than 1? And in fact, what's interesting about the forward backward Euler is you can basically show that if you let z equal lambda t, then you get this really nice picture, which is essentially for the forward Euler, let's just call that Euler, you ask the question, when is forward Euler stable? And it turns out it's stable only in a small patch of z here. And it's unstable everywhere else. So forward Euler is mostly unstable everywhere. Okay? Whereas backward Euler there's a small ball here where it's unstable and it's stable everywhere else. Okay, so this is this kind of interesting concept, which is if you're going to pick a scheme, backward Euler is stable almost everywhere except a small region. Forward Euler is unstable almost everywhere except a very small region. So what it's telling you is something like both of these are approximations with the same accuracy, right? This is important. These two schemes have the same accuracy for approximating this, but one has great stability properties as an algorithm. The other has terrible stability properties as an algorithm. And so when we start to compute, when you start to do Gram-Schmidt, when you start to do triangular orthogonalization using the householder, a lot of our algorithms are based upon iterative techniques. And if you iterate enough, the last thing you want to have happen is something like this, the iteration to blow up. Iterations generically often do, by the way.
I've got a question for you.
Iteration, things often blow up. And what you want to do, develop a numerical method so that when you do the iteration itself, the iteration scheme is stable. That is the entire point of this lecture. I'm going to stop it here. I'll send some notes out about this too. But that's the main idea. And then I'll take questions from here.